Now, for another set of input, ut equal to f to t, you have to again carry out the same set of operations. So it will become very repetitive. So instead of that, if I can find out a way of representing a relationship between the input function and the output function in a closed form, that is in a distinctive mathematical expression which describes the behavior uniquely, then it would be very easy. In the sense that if we know the input variable in the Laplace domain, then we can find out the output variable in Laplace domain very easily, right? If you know us, you can find out ys. Now you may again ask that, then in order to get yt, I again have to solve via the inverse Laplace transform and everything. Yes, that you have to do. But in the process, what we have done, we have minimized the effort of taking the Laplace transform of any entire equation and rearranging them in a suitable manner, like ys equal to gs into us. So this part is already done. It is simplified. Now the advantage is that, okay, in a sense that you have to again take inverse Laplace transform to get ys from this expression of gs into us. But it will be shown that for a particular class of system, just like a first order system or a second order system, only up to this, you do not have to solve this uh, this S domain expression of ys to calculate yt, because there are certain thumb rule or well defined characteristics present in literature, or characteristics have been found which relates the transfer function to the output directly. You do not have to solve for each and every case. What you have to solve? You have to solve for some different characteristic values or some parameter values, and from that parameter values you can clearly predict, or you can clearly obtain, not only qualitatively but quantitatively, what will be the response. So that is where, for first and second order system only, I again repeat, that is why this transfer function can be used as a very strong tool in predicting or analyzing first and second order system when subjected to different types of inputs. Okay, we just need to memorize or take help of some standard forms of the response given a particular first and second order representation of a system. Okay, we'll take an example while discussing about the time response part. So moving ahead, so let us go through some key aspects of transfer function. First, it is an operational method that expresses the differential equation which relates the output variables to the input variable. Right? How it expresses? It expresses the differential equation in Laplace domain or in S domain. Now, by using this concept or transforming the differential equation into S domain via Laplace transform, what it does basically, it converts a differential or integral differential equation into algebraic equation, right? Which can be easily solved, or it can be easily manipulated to obtain the expression for the output in S domain. And since it is in S domain, it is a frequency domain approach, right? Now, a major advantage is that from the transfer function, some of the information about the stability and the nature of transient response can be made readily available. That is, by looking at the transfer function, you can readily say whether the system is stable or not. You do not have to go for checking the Bibo stability condition and all. And you can clearly say what about the nature of the response for first and second order system. There's a very important aspect. Next, the transfer function, very important. It's a property of the system itself, and it's not dependent on the magnitude or the nature of the input. Whatever magnitude of input you give, whatever be the nature of the input, the output will depend on the transfer function, and the transfer function is unique. It doesn't change with the nature of input or the amplitude of input. So once you know the transfer function and you know the Laplace transform of input, you can easily obtain the Laplace driven representation of output, because the transfer function is an inherent property of the system and it doesn't change with time or type of input. So the direct consequence is that if you know the transfer function of system, then the response of a system can be studied for a variety of input. Another important aspect is that a transfer function doesn't provide any information regarding the physical structure of the system, right? So you don't get any information regarding the physical structure of the system, and it falls in the category of analogous system, where a differential equation may represent a mechanical system or electrical system or hydraulic system, but the equation or the nature of the equation is same. So in that sense, you cannot say just by looking at the transfer function whether it's a mechanical system or it's a electrical system. So it's a kind of a universal representation, only represents the input to the output. And on the other hand, if you cannot obtain the transfer function of a system in an analytical way, what you can do, you can obtain the transfer function via experimental method by carrying out some very simple or standard experiments. Now, obviously, there are certain limitations of this transfer function modeling. Now, what are those limitations? First of all, the transfer function is only applicable for linear time invariant system. It is not valid for nonlinear system or time varying system, right? Now, all the initial conditions need to be assumed to be zero, which is again a very restrictive or pessimistic approach, because you cannot always ensure that the initial condition will all be zero. That is, the system will be at completely relaxed state. That is very difficult to ensure in all the times. And finally, it is not very suited for systems having more than one input and or output. So it is much more suited for single input, single output system. For systems having multiple input or multiple output, is not very easily handled by a transfer function. Then the obvious question then comes, then how do we tackle such situations? So under such situations, what we normally do is that we take help of another approach which is much more generic, that is the state variable approach. What are the advantages of state variable approach? The state variable approach is applicable not only for linear, it is also applicable for nonlinear system. The state variable approach is applicable for time varying as well as time invariant system, whereas transfer function is only applicable for time invariant system. So state variable representation can encompass all the forms of systems that we have studied. Next, the major drawback of the transfer function, another major drawback is that it is only valid for zero initial conditions. That restriction is not there in a state variable model. In a state variable model, there is a provision that you can take into account any finite non-zero initial condition, right? And lastly, the state variable model is well equipped to take into account the multiple input and multiple output systems, right? Or more systems having more than one input and more than one output. So let us now take some examples of transfer function and how we can derive the transfer function. So let us start with a very basic example that we have started in the last class. So we have an RLC circuit where this is your V in and this is your V out. So we need to find out the transfer function, say GS as V out S by V in S. Now, uh, how should we approach the equation? First, let us write down the differential equation of the system, that is the KVL. So, if we consider the current IT here, then you can write Kirchhoff's voltage law as RIT L dit dt plus 1 by C integration I dt is equal to V in T, and the output equation V out T. Now, if you take Laplace transform with zero initial conditions, right? So that means I0 minus is 0 and V out 0 minus is equal to 0. The 0 minus depicts that just before the application of the input. Then from that, by taking the Laplace transform, what you can write is from the KVL R is plus SL is plus 1 by CS is equal to V in S, or V in S is equal to R plus SL. Similarly, from this we can write V out S is equal to 1 by Cs Is. So the transfer function IC stands for initial condition will be, after simplification, 1 by LC S square plus R by L S plus 1 by LC. So this is a transfer function of this RLC. And we have already derived the transfer function. Just to recap, if you have a system like this with this is in and this is E out 1, I will say E out, and this is being R and C, the current being I, we can derive E out S by E out in S with zero initial condition as 1 by, say I'm just putting R1 C1 E out 1, that's for sake of understanding, E out 1. So R1 C1S plus 1, right? Now if I have another such RC circuit, say R2 C2 E out T, and we have connected this with this, then we can, suppose I have not connected this, if there's an open, then you can write E out 2 by E into S with zero initial condition will be R2 CTS plus 1. Now my question will be, if I connect these two, then what will be okay, it's like a E out. What will be E out by E in S with zero initial condition? Any guess?
So we can divide both the equations by equation number 1 by equation number 2.
That means you want to say it will be like
Yes, sir.
R1 C1S into like this
No, sir, division, sir.
division. Why?
Because, sir, E out 1 and E in 2, these are equals, actually. So we can just cut that
No,
out.
in one is equal to E in, so
Yeah.
I think it will be multiplication. See,
Mm,
E out
হ্যাঁ হ্যাঁ হ্যাঁ, ইয়েস স্যার, ইয়েস স্যার, ইয়েস স্যার, ওটা মাল্টিপ্লিকেশন আছে, হ্যাঁ, ই আউট টু।
মাল্টিপ্লিকেশন,
হ্যাঁ, আপনি
তাই
ওই
না?
টুটা মুছে দিয়েছিলেন, আমি খেয়াল করিনি। হ্যাঁ।
হ্যাঁ হ্যাঁ, ওটা আমি টুটা জন্য বসে তাহলে আমার এইটা ইট উইল লুক বেটার।
হুম হুম হুম। হ্যাঁ স্যার, ওটা মাল্টিপ্লিকেশন হবে।
দিস ইজ ইউর ইন, this is your e out. It seems like this, na? But the problem is this is not correct. This transfer function will not be equal to this. There is a little trick. Whenever we're deriving a transfer function, say for in this case, we have seen or we have assumed that no power is drawn at this output side or from the output of the circuit. That is, it is in complete no load or open condition. No power is drawn from the output. But in this case, while deriving this individual transfer function, that condition was satisfied for each of these cases. But as soon as you cascade them, this is a cascade connection, what will happen? A power will be drawn from this output by this circuit. That means this second circuit will actually act as a load to this first circuit. And as soon as that happens, this very transfer function will not be valid because there is a condition that I have not mentioned so far. I want to mention it now that whenever you are deriving a transfer function from a particular output to any other input, your output should not be loaded or no power should be drawn from the output. That is, it should be completely relaxed. Since under cascade condition, the first part of the circuit is getting loaded. So this 1 by R1 C1s plus 1 transfer function doesn't hold. Right? So the question comes then, how can we derive the transfer function for this? Before going to that, I just have to add here that had there been an arrangement like this, like say a voltage follower or an isolation circuit, that means no power is drawn from this output, and such isolation circuit may be a simple voltage follower. So under such circumstances, what will happen? Since it has infinite impedance, no power, current will be drawn from this, right? So then this relation will be valid because we are not violating the basic principle of obtaining a transfer function, right? So again, the question comes in: if this isolation is not there, then how do we find out the transfer function? Then we have to resort to the very basic principle, or we have to derive the transfer function from the first principle. Like this is a first part of the circuit, this is the second part of the circuit, and we have E in and E out. And what we consider? We consider two currents here, say I1, I2, and we already have R1, C1, R2, C2, right? So what I'll do, I'll write down the KVL or to loop equations for loop I1t. I'll miss, I'll give a miss on the this t terms because obviously it's in time domain. What I can write, E in is equal to 1 by C1 integration See, I1 current is flowing in this direction, and I2 current is flowing in this direction. So in the sense of I1, what is the total current? This I1 minus I2 plus the drop in this resistance, that is R1 I1. Similarly, for loop I2t, what it will be? That will be R2 I2 plus 1 by C2 integration I2 dt. This, and there will be this capacitor again plus 1 by C1 integration I2 minus I1 dt is equal to 0. And we have the customary output E out is equal to 1 by C2. Now, assume all initial conditions to be 0 and apply Laplace transform. So from the first equation, what will get? EIS is equal to 1 by C1s I1s minus I2s plus R1 I1s. And from the I2 equation, what you will get? 1 by C1s, as I'm writing this first, I2s minus I1s plus R2 I2s plus 1 by C2s I2s is equal to 0. And from the output equation, we'll write E out s is equal to. Now from these three equations, you eliminate, say, I1, and this equation will finally reduce to the form like this. Sorry, it was E out. So up to this far, it was what was obvious, but just due to this loading effect, there will be this additional term. And this term represents the interaction between the two RC circuits or RC filters. And this can again be simplified to the standard form, that is 1 by R1, R2, C1, C2. তাহলে বুঝতে পারলে এই পার্টটা খালি অ্যাডিশনাল আসছে R1 C2s জাস্ট বিকজ অফ লোডিং এফেক্ট S স্কোয়ার প্লাস R1 C1 R2 C2 plus R1 C2 by R1 S plus 1 by. Now I am taking this particular form or representing the transfer function in this particular form because we have a standard definition of a transfer function in this form. We'll discuss about this later. What is the order of the system? This system order is 2. This is your second order prototype or standard form. Order 2 means it's a second order differential equation, and this number or order of the system depends on the number of energy storing element present in the circuit. Right? The total number of energy storing element is equal to the order of the differential equation. Now, coming back to a very interesting thing, that in order to derive this transfer function from the first principle or from the basic principle, what we encountered is a task of simplifying a set of algebraic equation. Although it may seem not very complicated because it's only a second order system, for a very higher order system, this might become very cumbersome. So what is the way out? Now there's another approach of deriving this transfer function. I'll first concentrate on electrical systems, and which will be equally applicable for a mechanical or any other system. Okay. So the thing is that this second approach that I want to discuss is something very interesting and a bit straightforward. What is that? That is called, the approach is called complex impedance approach. Now, what is impedance? Impedance, you can say it is the nature of retarding nature of any physical object to oppose any change in its present state or condition. So, how the complex impedance is defined? You can say any complex impedance Zs can be defined as the voltage across the element by current through the element with all initial conditions being 0. Now, there's very interesting one point I want to emphasize. Given any element Zs, a single port network, there is two terminals. This is your input, this is your output. We normally have two types of variables associated, and Zs represents, you can say, the transfer function. Now, it's a two terminal network. Then, how do we define this Zs as a transfer function or a ratio of input by output? For that, we need the concept of two more variables. One is across variable. There is a variable that appears across the element, and in this case, the across variable will be the voltage across the two terminals. Say if A is a input and B is the output terminal. So the across variable appears across the two terminals of a single port or two terminal network. And another variable is called through variable. What is this? This variable is a variable which enters the element from the input side and exits the element from the output side while its value doesn't change. The value it enters with through the input port, it exits the output port with the same value. So what will be the across variable here? Current, right? So the transfer function of an element, it may be, say, for electrical point of view, resistance, capacitance, or an inductance, will be given by this relationship. Similarly, the admittance, right? So it is basically output by input, and you may assume the through variable to be output or the across variable to be output, depending upon whether you are deriving the impedance or admittance. Now, with this in mind, for resistor, what will be Zs? R, because we know Vt is equal to Rit, so it will be simply R. Now for capacitor, what will be this? Zs. So we know for capacitor, Vt Idt, that implies Vs is equal to 1 by Cs. So Vs by Is will be 1 by Cs. And finally, for inductor, what will be Zs? We know for inductor, Vt is equal to L dit dt with zero initial condition. Vs will be Sl Is, so it will be Sl. So clearly, if we have a resistive element, we can replace them as R, capacitive element by 1 by Cs, and inductor by Sl. So with this, we can convert the entire network which is in time domain to its equivalent in complex frequency domain. And then what is the advantage? If you convert them into complex frequency domain and represent them in this form, any just for sake of simplicity, I'm taking this form where this is your Z1s and this is your EIS. See, each and every component is now transferred to their S domain equivalent. So you can write down the transfer function E0s by EIS is equal to Z2s. In this manner, each and every calculation will become very easy. Say, for example, suppose we have a circuit, RC circuit. In time domain, it is written as R and C and EI and E0. So I can readily convert it to its frequency domain representation as EI, E0. Capital means in S domain, R and 1 by Cs. So what will be E0 by EI? Without writing down the differential equation or without writing down the Laplace transform of KVL, that is Z2. What is Z2 now from this for this scenario? Z1 equal to R and Z2 equal to 1 by Cs. It will be 1 by Cs divided by R plus 1 by Cs. So multiply by Cs, 1 by RCS plus 1. Understood? Because in this scenario, in this case, this is your Z1, and this is your Z2. It's become so trivial. Say next example. Take an RLC circuit. What I'll do, I'll take this as Z1, this as Z2. So what is Z1? R plus SL CS. So you can calculate E0S by EIS is equal to Z2S by Z2S. What is Z2S? 1 by CS. CS multiply করে দাও. We multiply that. So you have S square LC plus RCS plus 1. So which can be equivalently written as 1 by LC S square. See how easy it has become? Because what I have done, I have transformed this time domain circuit to its equivalent complex frequency or S domain circuit. And then by simple law or the simple rule explained here, I have calculated the corresponding transfer function. Now let us try and apply this particular formula to our problem at hand. So our problem was given like this. R1, C1, R2, C2. This is your EI. This is E0. Now this can be equivalently represented in the form of complex impedance as right, where this is your EIS. Now I have to calculate E0 by EI. Now see, this is not in the standard form that we have discussed in previous two cases. So what we have to do, we have to recast this in somewhat simplified form. So what I'll do, I'll recast this in this form. I'll not try to এজগুলো লিখছি না, খুব redundant হয়ে যাচ্ছে এই জিনিসগুলো, কিন্তু মাইন্ড ইট when you are writing for the exam you should always mention this. এই এজগুলো কিন্তু মিস করো না, তাহলে তোমাদেরই ভুল হয়ে যাবে. So this is your E0. Is it EI? Now if you consider the current, say this is I, I1, I2. Okay. Now just to note down what is Z1. Okay, I'll write down these values later. Let's just derive these expressions. So from this loop, what you can write? First equation, I is equal to I1 plus I2, KCL at this node, right? Then you can write down for this Z2 I1 is equal to this. So if we eliminate either I1 or I2 from this expression, then you can represent both I1 and I2 as a function of I. So it will be like I1 is equal to, this will be Z2, right? So the current division is done. Now you can write E0. What is E0? This one, that is Z4 I2, that is Z4 into Z2 by Z2 plus Z3 plus Z4 I, and from the inner loop or this yellow loop, what you can write? EI is equal to Z1I plus Z2I1. So if you take replace I1 by I, so what you will get? Z1 by Z1 plus Z3 plus Z4 by Z2 plus Z3 plus Z4 I, right? Now from this last two equations, you take a ratio of E0 by EI. If you take simple ratio of these two, I will get cancelled out, and after just some simple algebraic manipulation, what you get is, now in our scenario, what are the different values? Z1 is R1, Z2 1 by C1s, Z3 R2, and Z4 1 by C2s. Now if you carry out this expression, then you will find out that it will lead to the same value that we derived earlier, that is 1 upon, আচ্ছা এখানে এসটা দিয়েছিলাম কি? হ্যাঁ। See, instead of going through this much of complicated equations where we have to eliminate each and every component or eliminate I1 or I2, this is another way of achieving the transfer function in a well laid out plan with the help of complex impedance. Okay. Now that we have some idea in a today I will not have much time. So what we'll do, we'll just conclude this part this to this lecture with a little introduction to block diagram. And in the next class, we shall use the concept of this transfer function and block diagram to develop mathematical model of some other systems like some mechanical system or things like that and derive the corresponding transfer function. Okay. So as we have seen that given a particular system, I can represent the system as this transfer function which relates this input Rs to its output Ys, or we'll be using the term Cs, such that Cs by Rs is equal to Gs, or Cs is equal to Gs into Rs. Now this equation is represented pictorially by this, and this is called the block diagram. See, in this case, what we have done, we have used this Z1s, Z2s. This is the block diagram representation of this individual elements. So, what is this block diagram implementation? Let us have a just brief introduction to that. Then we come back to the block diagram representation to price slide. So, in a modeling, we have just given introduction to the transfer function model. Now I'll come to the block diagram because that is very much related. The transfer function and the block diagram. So block diagram representation is basically a schematic representation or a topological representation of a system or a mathematical model. Now the block diagram is basically a pictorial representation that illustrates a functional relationship between its components. If it's a standalone block, then it's very trivial. Now, this block diagram is normally used to represent much more complex interconnection of components. So, if you can derive the transfer function of each and every component and you represent this interconnection via some block diagrams, then it will be very easy to apprehend how which component is connected to which component and how they are connected or how the signal is flowing between them. Right? For that, we have another part is signal flow graph, which is another extension of block diagram. So the basic thing is that it represents the components and illustrates the input-output functional relationship. So this is functional relationship means you can find out the individual transfer function related to input and output corresponding to that block. So a block diagram has different components. That is, these are the signals arrowed. There is a system normally represented like this, and this is a summing junction. করলে যে কি হচ্ছে বুঝতে পারছি। So this is summing junction where one signal is subtracted from the other signal, or it can be added to generate another signal, which is a combination, algebraic combination of these two signals. And then we have takeoff points where you can take off the signals. So all of them will have a same signal RS. So now let us use these components to develop a block diagram. To start with, let us consider this simple RC circuit. Now, how to develop the block diagram for this RC circuit? Let us see. Now, to develop a block diagram, we have to first convert this circuit either into the complex impedance form, or you can write down the differential equation or the equation from which the characteristics equation, that is current IT here is given by the voltage or potential drop across the resistance divided by the resistance. So it is V in minus V out by R, and this current on the other hand will determine the output voltage via this relationship. So these are the two important equations that represents the function of this circuit, RC circuit. Then you take Laplace transform of this equation, assuming zero initial condition. So you'll get Is is equal to V in S minus V out S by R, and V out S equal to 1 by S C S. Let us see how this equation can be represented via a block diagram. See, we have V in S. Now I have to subtract V out, and the output will be V in minus V out. Now if I divide this by R, that is if multiply by 1 by R, then I'll get Is. Followed? Then from this Is, I can calculate V out by multiplying this Is with 1 by Cs. And I get V out S. And this V out S can be brought back into the summing point as V out S. Now, this V out S being brought back to the input is called the feedback. Obviously, you can see. So, this is a block diagram representation of this RC circuit. Now, you might argue that this is something different from what we have developed so far, the transfer function, that is 1 by RCS plus 1. Yes, if you simplify this and find out the ratio between V out and V in, you get 1 by RCS plus 1. How? See, this is the standard form where RS is the input, CS is the output, HS is a feedback elements, comprises a feedback element, and ES is the actuating signal. There is a difference between RS and CHHS. So ES is given as RS minus CHHS, and CS is again a function of ES in the sense CS equal to GS into ES. Now from this two equation, you can write CS as GS into RS minus HSCS. So if you take CS all together to the left, we get CS into 1 plus GHHS equal to GSRS. So the transfer function CS by RS will be GS by 1 plus GSHS. In our scenario, what is GS? 1 by R into 1 by CS, that is 1 by RCS. And what is HS? 1. The GS is this, HS is this. So what will be the transfer function? Right? Okay. I just want to discuss an interesting phenomena that in this RC circuit, surprisingly, we came across this feedback. Okay, I don't know whether I've discussed it or not, but which is not very obvious. দেখো এখানে কিন্তু আমরা ultimately are getting at the same transfer function. This is unique. Fine. But why this feedback is coming? Any idea? এই ফিডব্যাকটা কেন আসছে আমি এঁকে দিচ্ছি এবার. So we started with a simple RC circuit. তাই তো? তো এখানে আবার এরকম একটা অদ্ভুত এস ডোমেনে যখন চলে আসছি, তখন আবার এরকম একটা অদ্ভুত সিচুয়েশন কেন হচ্ছে? একটা অদ্ভুত সিচুয়েশন কেন হচ্ছে? সিরিয়াস লেখা উচিত না, এটা ভি আউট লিখছিলাম। এনি আইডিয়া যে এই ফিডব্যাকটা কোত্থেকে আসছে আর আরসি সার্কিটে? আচ্ছা, কিরকম হয় বলো তো আরসি সার্কিটের রেসপন্সটা একটু বলে দিই। নিশ্চয়ই যাদের একটুখানি মনে আছে তারা বুঝতে পারবে, খেয়াল করতে পারবে। যদি এটা আমি ইনপুট দিই, জিরো ভি, এটা যে ইনপুট টাইম, আর নর্মালি ভি আউটটা ধর তখন জিরোই ছিল, এরকম হয়ে যায়, এক্সপোনেনশিয়ালি গ্রো করে। ঠিক আছে? So why does this phenomena happens like this? Why? Because if you look carefully at this point where we are given the input instantaneously, then at this point the rate of change is very high. In fact, it is highest. Then as the time progresses, the rate of change gradually decreases until it becomes exactly equal to zero once it reaches the final value. And this final value is again v. Why this phenomenon is actually happening? Because this rate of charging is a dependent function of the voltage across the capacitor. At the instant of switching, that is at this instant, Vc was 0. So, what was the current, charging current? I was V in by R. So, if I draw the current profile over here, so it was something like V by R. Now, as soon as a current starts to flow to the capacitor, Vc 0 plus becomes greater than 0, some finite value, and consequently I will become so this part is increasing, so current will gradually decrease, and as soon as it reaches the value of to control value, right, as soon as reaches the value, the V out t equal to V in t, or VCT, which is again defined as V out t is equal to V in t, that will implies IT will be equal to 0. So capacitor will be fully charged and there will be no potential drop across the resistance, because it is the potential drop across this resistance that determines the current flowing through it. So there will be no current flowing through it and the capacitor will remain fully charged. So that is why, see, as this capacitor voltage is increasing, this is continuously decreasing and we are getting a nature of curve like this. Right. So the feedback is coming in the sense the capacitor is providing a feedback. Okay, I have charged. I will not allow you to charge. দেখো আমার যখন কি প্রবলেম হয়, ধরো খুব খিদে পেয়েছে, ঠিক আছে, বিয়ে বাড়ি গেছে, খুব খিদে পেয়েছে, প্রথম দিকে আমরা প্রচুর পরিমাণে খাই। এবার যখন মোটামুটি পেট ভরে গেছে কিন্তু দুটো আইটেম খেতেই হবে, না খেলেই নয়, তখন কিন্তু আমাদের স্পিডটা কমে যায়। আর সেই অতটা স্পিডে আমরা খেতে পাচ্ছি না, আস্তে আস্তে খাচ্ছি, সময় নিয়ে খাচ্ছি, নিয়ে একসময় তো স্যাচুরেট করে যাব, যা ক্যাপাসিটি ফুল হয়ে গেল, তারপর তো কিছুই খাওয়া সম্ভব না। ক্যাপাসিটারও তাই, সেম ফেনোমেনা। The rate of charging depends on how much charge it acquires, and because of the law, as soon as there is some charge present in the capacitor, the potential that is generated across the capacitor due to the charge will tend to oppose any inflow of current. That is why the rate of charging will change, and when the capacitor is equally charged at a level of the constant input voltage, then capacitor will not allow any charge to flow, right? So that is why in this scenario the feedback is inherent in the circuit. So I'll just give you a task of developing, and I'll discuss in the next class the developing the block diagram for RLC series circuit that we have discussed today. এই সার্কিটের ব্লক ডায়াগ্রামটা বানিও। Okay.
Okay,
Okay,
sir.
so I guess I'll stop here. So I had some PPTs ready, PDFs ready for this block diagram algebra. So I'll cover that in the next class. Okay. So in the next class, I shall cover some non-electrical system or modeling of some non-electrical systems, or there is deriving the transfer function of some non-electrical systems, and the corresponding block diagram and the block diagram algebra, right? And I'll try to translate the concept of transfer function and find a correlation between the transfer function to state space, right? From transfer function to state space via this block diagram in the next class, right? Okay. If you have any query,
স্যার এই হ্যান্ড রিটেন নোটটা একটু শেয়ার করে দিতে পারবেন স্যার?
হ্যাঁ আমি তো করি তো, তোমার ক্লাসরুমে পেয়ে যাবে।
ওকে স্যার, ঠিক আছে।
সব হোয়াইট বোর্ডটা পেয়ে যাবে। I'll also share, I don't think I'll share it right now because that will disclose some of the tasks that is given you. So how much is possible I'll share with you the PPT
ওকে,
and the PDF.
ওকে স্যার, থ্যাংক ইউ স্যার।
Okay, okay. So we'll meet on Saturday again. This might happen this Saturday. I might have to shift my class to the evening, so might have to. So I'll let you know. Okay. Okay. Thank you.
ওকে স্যার।
Okay. Bye.